Good evening, everyone. I am Motilakshmi, second year metallurgical engineering. Today we are going to discuss on the topic of instability necking. Before going into the topic, first we have to know about necking. So necking is nothing but a reduction in cross-sectional area during tensile loading. While applying tensile load on the specimen, there will be some reduction in the area at some point, and then it undergoes the fracture. So the material reaches its limit of uniform plastic deformation. So this can be seen in stress strain curve, engineering stress strain curve, as you can see over here. After the elastic limit, there is some uniform plastic deformation, and then it undergoes fracture. So there is no immediate fracture, as it mentioned over here. It represents a geometric instability, which means there is as in the previous point we said that uniform plastic deformation. So which means after the elastic limit, there is some plastic deformation occurs in the specimen, but which is uniform. After the necking point is reached, the material undergoes fracture. So that's what it's saying, geometric instability, which means there is some instability in the geometrical dimension of the specimen, rather than immediate fracture. So now we'll study about engineering stress strain curve. So first of all, before going into necking, so we need to understand some terms which is known as ultimate tensile strength, which is the peak load carrying capacity, which means the peak load until which the material does not undergo fracture. So this is the point. The material can withstand the load. So point of instability. So necking begins exactly at the UTS, which means at this point the necking begins to start. Which means at this point, after this point alone, the material starts to fracture. At this point, complete fracture of the material can be observed. So post UTS behavior, which means look at this curve. As you can see over here, there is some decrease in the stress, which is due to the original area. As we know that the ultimate tensile strength is measured by using the original area, and also the engineering stress strain is only based on the original area, not the instantaneous area. So as we know that the necking is basically a reduction in area, so the original area gets reduced. So because of this, the stress also gets reduced, and this is the reason why the curve is declining over here. Okay, now let's understand a few more terminologies, which is hardening, that is strain hardening, and geometric thinning. So strain hardening is nothing but when a material is gets deformed, the material gets more stronger, which is when the material gets deformed, the ductility of the material increases, which reduces the strength, but it increases the hardness. That is related to the proportionalities. And then this is geometric thinning. The cross-sectional area reduces as length increases. As we know that while applying tensile strength, the length of the material will be increased, where the area of the cross section is reduced. As for this, I'll show you an image. Yeah, as you can see over here, while applying the tensile load on top and bottom, the length alone gets increased. While applying the load, the area of cross section is getting reduced. So this is what is explained over here. And yeah, this is the geometric thinning. And now why the terms are using over here is because the necking condition occurs when the rate of area reduction outpace the rate of work hardening, which means when the cross-section area reduction is increased than the strain hardening, then necking condition, that is necking, takes place. As we see over here, when the cross-section area reduction is increased, that is cross-sectional area is getting reduced more than the strain hardened, then the necking will be done and the material gets fractured. This is what is explained over in the slide. Yeah, this one. Next, moving into the analytical condition for necking. We know that post condition is stress by strain, true stress by true strain, and power law, also called as Holloman, which relates true stress and true strain, and also the strain hardening exponent. So necking occurs when the true strain equals the strain hardening exponent. So as you can see over here, the relation between the strain hardening and the strain hardening and the true strain. So because of this, the necking occurs. And then there is a branch in necking, I mean the types of necking, which is diffusion and localized necking. So diffusion necking is nothing but width of the neck is greater than thickness, as this can be seen commonly in cylindrical bars, as we said that the width of the neck is greater than the thickness, which is, this is the width of the neck and this will be the thickness of the neck, as I mentioned over here. This is the thick width of the neck and this will be the thickness of the neck. So when this increases, necking will occur. This is the diffusion type of necking. In this type of mechanism is followed, and in localized necking occurs in thin sheets at a specified angle, approximately 55 degrees. As in localized necking, this will occur only in thin sheets, as the thickness is not considered, as we already know that the thin sheets thickness is very very small, so will not consider that, but the neck will occur at the width of the specimen. As you can see over here, it's the width of the specimen. So this, and also this will occur approximately in a specified angle, that is 55 degree, approximately 55 degree. So this is called as localized necking. As you can see over here, the necking occurs at some angle, and in diffusion necking you can see that the width is larger than the neck. So this is what is explained over here. And mostly failure mode, in this the failure mode is more in localized necking, as it leads to tearing and fracture, and diffusion necking is very rare. And yeah, we'll come to an application, which is aluminum beverage cans. So manufacturing process, the aluminum beverage cans are manufactured by deep drawing and ironing. So deep drawing and ironing are process by which aluminum beverage cans are prepared, and deep drawing is nothing but by compression mode we will get compression, and by ironing we'll get the scans. So because why this necking is instability necking is used over here is because the material must have high N value. That is, the material should have strain hardening, more strain hardening to avoid necking during the punch. When the cans are punched without undergoing necking and fracture, it should withstand that. So the material should have high strain harden, that is high N value. And then so what is the result what we that we have got by this in using in producing aluminum beverage cans is tearing during drawing is usually a result of reaching the necking limit prematurely. So in drawing, tearing occurs. So because of this, the necking limit is reached prematurely. So with this, we'll get a high N value. And the next application is earth engineering. So it's nothing but using a steel rebar. Steel rebar is nothing but this one. So this allows this in this necking will occur significantly. So as you all know that this steels are used in making of buildings. So why this type of steels are used in the building is because while in earthquake this necking in this the necking will starts and undergoes massive deformation. So as there is some question arise that massive deformation occurs and why we are using this. This is because visible necking can be produced in this steel before going into failure. So while necking happens, there will be some what you can say, there will be some occurrence or signals in the buildings. So that will be a warning for to evacuate. Yeah, this is the reason why we are using the steels, this type of steel rebars in making up of buildings. So next, not only the necking and the various factors affecting stability is strain rate sensitivity, which is denoted by M. So high M value can delay necking. So when the strain rate sensitivity is more, the necking delays, which means the material even in high strain rate, it can even withstand some small strain deformation. So this is called as superplasticity. So in which the necking delays due to the high value of M and also temperature. So increasing heat typically increases ductility but decreases strength. As I said in the first itself, as I said in the first slide itself, that when ductility increases, the strength will decreases, and because of this, the hardness will increase. That was said here. When the heat increases, the ductility increases, but the strength decreases. So this will also affect the stability of the material. So material impurities, yeah, this is the main reason. So no material can exist in pure form. So there is some impurities. So like non-metallic inclusions act as nucleation site for localized thinning. So by adding impurities to the material nucleation occurs, and which will make localized thinning occurs. So because of this also the stability gets affected. So conclusion, yeah, necking is a critical transition from stable to unstable plastic flow. Yeah, as I said in the stress strain curve itself, that it's between, yeah, this point and this point. This critical transition is known as nicking. So yeah, predicting nicking via concealer is essential for metal forming. So why we have to know about nicking? So we must know about nicking because of metal forming. For metal forming, nicking is more efficient factor, as the materials can deform in a small nicking itself, or it can withstand a large strain rate. So we have to know that, and should make the materials according to that. So this is another one point for knowing about nicking. And the next one is understanding instability is the key to preventing manufacturing defects and ensuring structural integrity. Yeah, this is what I said. So by understanding the instability alone, we can be able to make a material according to that. So what are the materials can fracture at even a small nicking, or in a short period of time after nicking. So what are the materials that can be able to withstand, how long the material can withstand after nicking. And so because by this learning alone, we can be able to make a material according to that. And also, the what are the materials should have at what necking values. So for example, material stainless steels, for that is cooking purpose utensils, as we have kept in a stove, so it will increase the temperature. So it may occur to failure. So according to that, we have to make the material, that is, it should withstand a higher temperature. So according to that, we should make a material. So for this also, we have to understand the instability. So this is the key to understand this. And this is all about instability nicking.